Hello friends, I am Professor Swanan Dogre, and in this lecture we are going to study the common emitter configuration of BJT. In last video we have studied the common base configuration, and here now we are going to study the common emitter configuration. So out of common base, common emitter and common collector configuration of this BJT, common emitter configuration is widely used. Because if you consider the common base configuration, in common base configuration current gain is alpha and it is less than unity, and in common emitter configuration current gain beta it is moderate. In common collector configuration the current gain is gamma, and which is the highest current gain out of these three configuration. But if we consider the voltage gain, it is in reverse manner. The voltage gain of common base configuration is highest, voltage gain of common emitter configuration is moderate, while the voltage gain of common collector configuration is the smallest. So that is why if you consider the common base configuration, out of the current gain and voltage gain, the current gain is less, and if you consider the common collector configuration, the gain is less. So that is why the power gain of common base configuration and common collector configuration, it will be less. But if you consider the common emitter configuration, the current gain and voltage gain, they are moderate. So that is why the product voltage into current, that is power, it is highest. So that is why as in common emitter configuration the current gain and voltage gain, they are moderate, it is widely used configuration among three configuration. So CE configuration is widely used, and obviously in between the NPN and PNP transistor, the NPN transistor is widely used because in NPN transistor the majority charge carriers are electrons, and electron mobility is greater than the hole mobility. So that is why in practice you will find the common emitter configuration with NPN transistor which is most widely used. Now I will draw here the circuit diagram of the common emitter configuration considering NPN transistor. As the name indicates, it is common emitter configuration, so that is why emitter is common terminal. So emitter we have to show on downward side. Out of remaining two terminals, that is base and collector, collector is having more area, so that is why collector at output side, that is right side, output side, and the third terminal which is base it is at input side, means left hand side. So I'll rotate, I'll flip the symbol of this transistor so that the base will be on left hand side. So this is base, then I'll have the emitter and the collector, and as it is common emitter configuration, emitter at downward side and collector on right hand side. So I'm having collector, then here I'm having emitter, then this is base. So this is the symbol which I have shown for common emitter configuration. Now there will be one resistor in series with this input terminal, that is RB. Then there will be a supply between input and common terminal. Then there is resistor in series with the output terminal RC, and there will be supply between this output and common terminal. What I have to do, it is NPN transistor, it is NPN transistor, NPN transistor, and the basic function here we have using this as an amplifier, so that is why it should operate in active region, and in active region base emitter junction should be forward bias. So P type should be at higher potential, N type should be at lower potential, so that is why it is plus minus, and this supply, name of this supply is VBB. Then there is no direct supply between collector and base, and we have to reverse bias the collector base junction. In my previous video I explained this, how to reverse bias this collector base junction with the help of the supply between the collector and emitter, and obviously it is plus minus VCC. So this is the circuit diagram. Here the input current is IB, then the output current is IC, and the total current is I. So in common emitter configuration the input current is IB in microampere, the output current is IC. The input voltage here, it is applied between the input terminal and common terminal, so that is why it is VBE, and the output voltage, it is the applied between, it is measured between actually collector and common terminal, that is VC. So this is all about the circuit diagram of common emitter configuration. Now let us draw the input characteristics of common emitter configuration. So here I'll draw the input characteristics. So as we know that input characteristics is the graph of input current on y-axis versus input voltage on x-axis at constant values of output voltage. So here if I draw the input characteristics, so the y-axis is the input current, that is IB in microampere, then the input voltage is VBE in volt, and I can show here the values, say it is 0.2, 0.4, 0.6, 0.8, 1 volt, right? And the current 10, 20, 30, 40, 50 microampere. If you refer different books or literature, you may have slight change in these values, because in that the consideration is that their VCC, VBP, RB, RC value may be somewhat slightly different. So that is why you may have change in these values. Now here I am showing the characteristics for the different values of output voltage. Here the output voltage is VC. So I'll show here the characteristics. First characteristics you can see here, then the second characteristics, then the third characteristics, and these are the three different characteristics, input characteristics of common emitter configuration, which are drawn at different values of VC. So this is equal to, VC is equal to say 2 volt, then VC is equal to say 6 volt, VC is equal to 10 volt. So these are the input characteristics. Now if you consider any one characteristic, say at VC is equal to 2 volt or at 6 volt or 10 volt, here if you increase the voltage, you are getting the increase in the current. Up to certain voltage, the input current is not flowing. So if you refer this characteristics resembles, it is same as that of the forward bias characteristics of PN junction. And obviously in between base and emitter there is one PN junction in transistor, and this PN junction in the circuit, it is forward bias. So that is why this input characteristics is same as that of the forward bias characteristics of PN junction. Now if you consider the constant value of input voltage VB, let us consider it is say 0.6 volt. At constant values of this input voltage, say at 0.6 volt, if you consider the different values of the current, right? So I'll get the different values of current. So this is at B point, this is at C point. So what is the conclusion? If you increase the output voltage, that is from 2 volt to 6 to 10, what is happening actually? If you increase this output voltage between collector and emitter, right, the collector will be at more higher potential as compared to emitter. So if the collector potential is increased, then the collector base junction, its biasing, which is already reverse bias, but this reverse biasing voltage will be also increased. And we know that with increase in collector base voltage, what will happen? The width of depletion region near to the collector and base, it will increase. So the width of the reverse bias collector base junction, it will be more in base region. So the resultant effective base area, its width will decrease. And if it is decreased, what will happen? The base current will also decrease. So that is why the same observation here we are getting, with increased values of VC, the effective base width will decrease, and there is decrease in the, with increase in output voltage, there is decrease in the input current IB. And this is known as base width modulation. This is known as base width modulation. We know that the current gain of the common emitter configuration is beta. Beta is equal to the output current, which is IC, divided by input current IB. So if you increase the output voltage VC, what will happen? If output voltage is increased, then there will be the reduction in the effective base width, and it will decrease the base current. And if base current is decreased, what will happen? The beta will increase. So this is called base width modulation. This effect is called base width modulation. Now if you consider a single characteristic, say at Vc is equal to 2 volt, if I consider any 2 points on these characteristics, say P and Q, these are 2 points. So if I take the projections of this P and Q point on voltage axis and current axis, what I am getting here? Here I am having the change in input voltage, and here I am having change in input current. So this is delta IB, and this is nothing but the delta VB, change in the input voltage and change in input current. So what is resistance? Resistance is nothing but the voltage divided by current. Then what is the input resistance in this common emitter configuration? It will be the ratio of input voltage divided by input current. Now there is one term, it is called dynamic input resistance. Dynamic means over a range of voltage, over a range of current. Obviously it is dynamic input resistance means over a range of input voltage and input current. So that is why dynamic input resistance Ri of common emitter configuration, it is delta change in voltage, that is delta VB divided by we are having delta IB when the output voltage Vc is equal to constant. So this is the dynamic input resistance. So this is all about the input characteristics of the common emitter configuration. Now friends, let us study the output characteristics of the common emitter configuration. We know that output characteristics is the graph of output current on y-axis versus output voltage on x-axis at constant values of input current, So here if I show the axis, this axis, vertical axis, will be the output current. In common emitter configuration, the output current is IC, which is in milliampere. Then I am having the output voltage, which is nothing but Vc in volt. And I'll draw here the different characteristics for constant values of input current. The input current is IB. So I'll draw the values for IB is equal to 0, IB is equal to say 20 microampere, 40 microampere, then 60, 80 likewise, right? So see the characteristics. Here first characteristics, which is equal to IB is equal to 0, then IB is equal to say 20 microampere, right? Then IB is equal to say 40, IB is equal to 60, IB is equal to 80. Likewise, you can draw the characteristics, right? And here, if I show this VC can be say 0, then you can have 2 volt, 4 volt, 6 volt, 8 volt, 10 volt, right? Then the values of IC in milliampere, say it is 1 milliampere, then 2 milliampere, then 3 milliampere, then 4 milliampere, then 5 milliampere. Likewise, you can increase it. You may have slight change in these values of voltage and current based on the values of VCC, then the value of VBB, RB and RC. So the first characteristics, it is for IB is equal to 0, then IB is equal to 20 microampere, IB is equal to 40 microampere, IB is equal to 60 microampere, IB is equal to 80 microampere likewise. So here I'll show the different regions of operations of BJT on this output characteristics of common emitter configuration. So for that, let us consider this circuit diagram. In this circuit diagram, with the help of this VBB and VCC, the base emitter junction is forward bias while the collector base junction is reverse bias. Now if I open this VBB, means base is open, no supply is connected between base and emitter, means base terminal is open, what will happen? The current IB will be equal to 0 because it is open loop now. There is no closed path. So current IB will be equal to 0. So what will happen? If IB is 0, no current will flow through the base terminal, and hence the base emitter junction is now reverse bias. Already collector base junction is reverse bias, and if you remove this VBB, base will be open, and the base emitter junction, it will be also reverse bias, and if both the junctions are reverse bias, transistor will operate in cutoff region, and in cutoff region it acts as an open switch. So on these characteristics, the region below IB is equal to 0. You can see here it is cutoff region, and in this cutoff region transistor acts as an amplifier, it acts as an open switch. Now to further explain, let us consider the output side loop of this circuit diagram of common emitter configuration. So there is one closed loop which consists of this supply VCC, then this resistor RC. There will be some drop between collector and emitter. So if you apply the Kirchhoff's voltage law to this output side loop, you'll get minus plus VCC, then plus minus IC into RC, and this plus minus VC is equal to 0. Hence VCE is equal to VCC minus IC into RC. In this, VCC is constant, RC is constant. IC, it depends on the input parameters, which we'll see. In common emitter configuration, the current gain beta is equal to output current IC divided by IB. Now what will happen? If you increase this base current, collector current will also increase, and if collector current is increased, what will happen with VC? VC will decrease. So same here we can observe, if I increase the base current, that is input current, then there is decrease in the value of the output voltage VC. So within this region, that is above IB is equal to 0, we are having this the active region. So this region here, it is active region, and in active region the output current is almost constant for given value of input current, though there is increase in VC. See, though we are increasing the VC, the output current IC, it is not changing. There is slight change, right? But if you increase the base current, what is happening? With increase in base current, collector current is increasing. So that is why within this active region, this current gain equation is valid, and there is no effect of output voltage on output current. The output current is controlled by only input current. Hence that is why the BJT is current control device, and within this region it acts as a constant current source. Now what is happening, if you further increase, if you go on increasing the input current, IB, the collector current will also increase, and if you modify this equation, right, the collector current, it is equal to the VCC minus VCE divided by the RC. Out of this, VCC and RC are constant, and IC, the changing parameter will be IC and VC. Now let us consider, if you increase the base current, what will happen? Collector current will also increase, and hence the collector to emitter voltage, it will decrease. So if you further increase the IB, IC will increase, the collector emitter voltage will decrease. A point will reach. Beyond that, you cannot increase the IC, though you are increasing the IB. Why? Because that value of IC, maximum value of IC, that is known as IC saturation, it will be equal to VC saturation, VCC minus VC saturation divided by RC. VCC is constant, RC is constant, and for saturation region the value of VC in common emitter configuration is 0.7 volt, right? So IC saturation will be equal to VCC minus VC saturation divided by RC. VCC is constant, RC is constant, and the minimum value of VC after decreasing it will be equal to its saturation value, which will be typically 0.7 volt. So that is why the maximum value of IC that can be obtained, it will be given by this equation, and it is called saturation. So this is the point when VC is equal to its saturation value, a point will reach that IC will be at its maximum value. It cannot increase further, though there is increase in the base current. So that is why this relation, current gain relation, it will not be valid now. It will not be valued now. Though you are increasing IB, there will not be increase in IC. So this is called saturation. So transistor has reached to the saturation level, right? So if you go on increasing IB, a point will reach where what will happen? The VC value will be nearly equal to the 0.7, and though there is increase in IB, the collector current not increase. That region, right, is shown by dotted here, dotted region, and it is called saturation region. The current gain relation is not valid in saturation region. So this is a saturation region. Now here, if you consider the value of VC for saturation region, it is very small, near to 0, and typically it is 0.7 volt for the common emitter configuration. Now let us consider the cutoff region. In cutoff region, if I consider this equation, output loop equation, VCC is equal to minus IC RC minus VC is equal to 0. What is cutoff region? As we have shown, cutoff region means base is kept open, means IB is 0, and if IB is 0, from this equation of current gain, collector current will be also 0, and if collector current is 0, this term will become 0. So for cutoff region, VCE cutoff value is equal to VCC. So this is the value of VC for cutoff region. So here we have seen the what are the values of VC for cutoff region. For cutoff region, VC is equal to VCC, and for saturation region, the value of VC is nearly about 0, that is equal to near about the 0.7 volt. Here, now let us see the dynamic output resistance. The dynamic output resistance, it is nothing but delta RO. It will be the ratio of change in output voltage, that is VC here, and change in output current, that is IC, at constant values of input current. So that is dynamic output resistance. So this is all about the output characteristics of the common emitter configuration. Thank you.